Hello, welcome to the presentation Automation of Visual Positioning of Unmanned Vehicles based on an adaptive Cascade algorithm. Our team brings together specialists from the National Aerospace University, Kharkiv Aviation Institute and the Azerbaijan Technical University, who works together to create innovative navigation methods. The main purpose is to develop a software architecture in Python for automated visual positioning of UAV based on an adaptive Cascade algorithm. The principle of operation of which is focused on modularity, reduced computational load, and intelligent adaptation in real time. In addition, a parallel direction of research is to assess the accuracy and performance of the proposed algorithm in real conditions, as well as analyze objects around UAV to determine the characteristics of its position using visual position methods. Methods that serves as the basis of creating an adaptive algorithm, proximity, centroid, very centroid, and lateration. The logic of functional elements is implemented in a modular structure with iterative optimization of calculations, which allows for the unhindered use of such a system on drones with limited capabilities. The proposed software has a three-level structure, the blocks of which are presented in the diagram on the left. The graphical user interface level contains widgets that allow the user to interact with the application. The application logic level contains functions responsible for the detection, analysis, and process modules of the received data, and the surface level provides interaction between the system blocks in real time. The main options for modeling an autonomous system are presented in the diagram on the right. The user can select display parameters when setting detection ranges and apply visual navigation methods to the video stream, view information on the dashboards in real time, and export the reports to .txt or Excel files. The following flowchart, which is presented on the slide, allows you to understand how the process flow in the software application occurs. Among the components are the launch and initialization of components, detection of objects, application of selected local navigation methods, measurement of their performance, export and update of the interface. The user doesn't have direct influence on the internal functions of the algorithms or commands for the computing core, since the system is able to work autonomously with any number of objects around and different sequence of their detection. Instead, the application of the certain visual navigation method is based on the condition of detecting a sufficient number of landmarks around the UAV and depends entirely on the user choice. The images on the slide demonstrate the operation of the Auto UAV Navigator software application when performing two different tasks. In the first case, image on the left, objects are detected and their location is established using the visual navigation method selected by the user. The images on the right side display a pop-up interface window that works in a parallel stream and displays the status of the video generation process in real time for simulation and experiment in a complex environment. Architectural decisions are made taking into account the requirements for performance, reliability, security, and the possibility of further expansions of the system. Thus, the principle of modularity of components was laid at the heart of the system development, which allows for the unhindered scaling of the system in the future, as well as making it adaptive to changes in both environmental conditions and tasks. The presented diagram illustrates the structure of the system and the layering of components in their logical sequence from the moment of launch to the completion of program execution. Among the presented components, calculation and processing functions, data arrays and dictionaries, as well as interface components that are added to the system when they are directly needed. The line chart on the left shows the results of checking the accuracy of the methods in determining the current position of the quadrocopter. As we can see, the determining position of the quadrocopter calculated using centroid and proximity are quite close to the real position of the object in most cases. Unlike the previous ones, the calculation of the quadrocopter position in space using the visual orientated methods, weighted centroid and lateration demonstrate higher accuracy rates due to weighting coefficient and solving the nonlinear system of equations by the least squares method. The bar chart on the right illustrates the distribution of error values obtained during the process of detection various landmarks around the UAV using a color mask. The bars clearly demonstrate the variability of color recognition accuracy in the HSV space, allowing you to identify marginal deviation as well as estimate the average level of error at the stage of detection each object. To assess the performance of the developed software, the use of the main hardware resources of the system was monitored. In particular, the Central Processing Unit (CPU) and Random Access Memory (RAM). The pie charts show the shares of resources used by the program during the operation of each of the visual navigation methods. When using each visual positioning methods for 30 seconds, with the minimum number of landmarks required for its operation, it became known that the minimum value of RAM consumptions is for the use of the proximity method and is 160.5 megabytes and has an impact of the processor which is estimated at 8.4%. Lateration has the maximum RAM reservation indicators 252 megabytes and the impact of the processor is 28.7%. In both cases, the value of a moderate load on the processor cores in the context of determining the current position of the quadrocopter DJI Tello EDU in the local environment. Therefore, the proposed software application Auto UAV Navigator, which provides automation of the local positioning process based on a Cascade algorithm, is an important contribution to the research, as it allows not only to detect objects and calculate their position based on the basic methods of visual positioning, but also to choose the most accurate one of them, as well as to conduct modeling in complex environment. Among the future direction of the context of the research, the following can be noted. Development of method for compensation and error correction using statistical methods or machine learning, integration of additional sensor data, inertial measurement unit or data from depth camera, scaling experiments to more complex environments, including dynamic scene, external obstacles, and changing lighting conditions. This concludes the presentation of the research results. Thank you very much for your attention and the interest in this research.